Hello, my name is Kitty Escrizzi, President of the University of Michigan Mars Rover Team, and I'm excited to welcome you to the 2019 System Acceptance Review for the University Rover Challenge. This year's rover builds on our prior successes while introducing changes based on lessons learned in past competitions. In this review, we will showcase the mechanical, electrical, science, and software capabilities of our system. Additionally, we will detail our completed and planned testing to ensure full system readiness in May.
The mechanical foundation of the rover is composed of the chassis and mobility subsystems. The carbon fiber chassis is divided into modular sections for quick reconfiguration between missions. Our differential bar has a pivot at either side to reduce the bending moment seen in the bar. Its length is adjustable to ensure the chassis is level with the ground at all times. The entire rover is supported by adjustable shocks, which interface with a linkage system to absorb both downward and frontal impact. We chose a ride height of 18 inches and a wheel diameter of 12 inches to surmount large obstacles. This year, we have revamped both the design and control scheme of our robotic arm. Our 40-inch, 7-degree of freedom arm is composed of carbon fiber tube sections and controlled using inverse kinematics for fluid, user-friendly operation. The end effector can open up to 6 inches using a lead screw to provide substantial grip strength and precise tool positioning. 2 intersecting laser pointers aid the operator in positioning a solenoid to type on a keyboard. Additionally, Phillips and hex head screwdriver bits can be swapped remotely to screw in a bolt.
The electrical system controls power and logic signals for all components on the rover. Our custom power distribution system ensures that each mission can be completed with a 544 watt-hour LiPo battery. The NVIDIA Jetson TX2 was chosen as the main onboard computer to process all sensor information and enable rapid autonomous decisions. From testing with our 900 MHz radios, we have shown that communication between the base station and the rover is maintained over operating distances of 350 meters or with line-of-sight obstruction.
We have developed a comprehensive rover operation suite to enable smooth and user-focused teleoperated control. Through a graphical user interface, rover operators have easy access to the rover's position and orientation on a map, a live camera stream from one of 8 onboard cameras, and other important diagnostic readings from the rover. The interface and control schemes are quickly adaptable for different operations, such as switching between inverse and forward kinematic control of the arm. Our autonomous navigation system utilizes a state machine to map its current state, odometry, and computer vision data to an action and a new state. The system obtains accurate odometry by feeding input from a 9-axis IMU, GPS, and wheel encoders into a custom sensor fusion algorithm. We use a stereo camera to identify tennis ball candidates in view using color and depth data. Candidates are confirmed by a learned model for high reliability tennis ball detection. The depth data from the stereo camera is also utilized by obstacle detection. The autonomous navigation system has been tested extensively in a custom-built simulator, as well as on a physical course of GPS waypoints and tennis balls for the autonomous mission. To prepare for the extreme retrieval and delivery mission, we have mapped out a 1-kilometer course at a test facility that includes a rock garden and objects that we expect to retrieve in the field. For our operators to become more adept at arm control in the equipment servicing mission, we have designed and constructed a mock lander with all components described in the rules.
For the science mission, we have developed a suite of instrumentation and biochemical assays to determine the presence or absence of life. A 3-axis instrument positioner mounts below the chassis for precise pointing of a high-resolution digital microscope and a custom-built Raman spectrometer at rocks of interest for in-situ analysis without significant alteration. The microscope images sites in search of gross morphologies indicative of fossilized or living microbial communities, while the Raman spectrometer uses a 532 nanometer laser to detect chemical compounds associated with organic matter and organisms. The next element of our life detection strategy targets biomolecules and biomarkers in soil samples. The sampling system features 2 identical drill and vacuum mechanisms to transport particles to sterilized boxes, each isolated to prevent cross-contamination. The boxes house tests for DNA with fluorescence imaging, protein with Burette's reagent, and ammonia with indicator strips, all of which can be monitored live from the base station. These tests allow us to detect biomolecules and biomarkers associated with life. We have validated these methodologies by testing on sterilized rock and soil samples, as well as fossilized bacterial colonies and Utah desert soil.
At this point in the season, we have completed manufacturing, assembly, and initial full system testing. Between now and competition, we will practice each mission extensively at an outdoor test facility under competition-like time constraints and scoring schemes. We are thrilled with our team's continuing progress and confident that our rover will be competitive in the 2019 University Rover Challenge. On behalf of the Michigan Mars Rover Team, thank you for your consideration, and go Blue!